Welcome to FYI, the 4-Year Innovation Podcast. This show offers an intellectual discussion on technologically enabled disruption, because investing in innovation starts with understanding it. To learn more, visit arc-invest.com.
ARC Invest is a registered investment advisor focused on investing in disruptive innovation. This podcast is for informational purposes only and should not be relied upon as a basis for investment decisions. It does not constitute, either explicitly or implicitly, any provision of services or products by ARC. All statements made regarding companies or securities are strictly beliefs and points of view held by ARC or podcast guests, and are not endorsements or recommendations by ARC to buy, sell, or hold any security. Clients of ARC Investment Management may maintain positions in the securities discussed in this podcast.
Welcome to ARC's 4-Year Innovation Podcast. Today, we've got a great guest. We have Dr. Christyl Johnson, who is the Deputy Director for Technology and Research Investments at the Goddard Space Flight Center at NASA. And you probably know Tasha and myself, but if not, we'll give another quick intro. I'm an analyst at ARC Invest, who works closely with Tasha on our autonomous technology and robotics team. And I focus on space, robotics, and energy storage. Tasha?
Hi, everyone. Tasha Keeney here, analyst at ARC. I work with Sam. I focus on autonomous technology in all machine types and 3D printing.
But no one really cares about what we do. Dr. Johnson, what do you do as the deputy director? And how did you come to work at NASA? I feel like that's every kid's dream is to grow up and be involved in space. NASA, not just a cool fashion brand, right? They're doing amazing things in space. How did you wind up there?
Yeah, so I actually started as an intern. I had an opportunity to do an internship one summer. And, at first I was thinking it was part of this Lincoln Aerospace Engineering Recruitment Program. We were required to do an internship program at one of the NASA facilities for the summer. And my particular internship was at Langley Research Center in Hampton, Virginia. And they told me I was going to be assigned to a physics lab. And so I was like, physics? What in the world? Who would want to work in physics? And what do you do working in a physics lab? So I was like, okay, whatever. In my mind, I have always believed that there is always a silver lining in every single cloud. You just have to look for it, right? So I kept telling myself, okay, Christyl, just look for that silver lining and see what you find. So I get to the lab at Langley, and there was one of those danger, radiation inside, laser radiation inside. And so when they opened the door, they said, okay, put these goggles on. Don't lean down to the level of the table because there's stray laser beams going around the room. And if it zaps you in your eye, it can blind you. And I was like, what in the world have I gotten myself into? I was like, I cannot believe this. So then I go in further. And this was back in the day when we wore the white lab coats and the sleeves were pretty big and dangly. So the guy was leaning over the laser table and he was adjusting one of the knobs of the laser mirrors. And all of a sudden, pop, 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 and there was smoke. He got his sleeve in the way of the laser beam and there was smoke coming from his sleeve. Then I was like, yes, this is the field for me. You get to shoot lasers around the room and put holes and stuff. So I was really, really excited after that to kind of see what this was all about. And every single day when I'd go to work, it was never the same thing twice. So there'd be some days where we're in the lab, trying to figure out what to do with this laser, because we investigated whole new laser crystals to develop new lasers for different applications. And so we couldn't get something to work. We'd go to the mall. We'd be sitting there, people watching and talking about folks. Somebody get an idea. We'd jump in our cars and head back to the lab and make it work. Or we'd, be in somebody's boat out on the water. And we dive in and do some swimming around, and we all had our laptops on the boat. So we come back on, somebody has an idea, we're doing the work. That was the most thrilling and fun kind of lifestyle, because as an engineer, you're paid to think no matter where it is. And NASA is one of the most innovative environments for you to really be able to think and create. That's why we're the best place to work in the federal government for 8 years standing. It's just a really cool, innovative place to be. that's how I got into the field.
Wow. Well, you just sold me on NASA. I feel like you're gonna get a lot of applications after hearing this.
Yeah.
The boat's not included though. I don't think.
Yeah. So what I do at NASA now, I think I have one of the funnest jobs in the whole wide world because I get to do what I call engineering. And so I get to actually work with a group of scientists to actually envision the missions of the future in earth science, astrophysics, heliophysics, and planetary science. I mean, far out missions, things we've never been able to do before. And then I'm responsible for putting together a portfolio of technology investments. So those kind of technologies that are leading edge, that are going to enable not just a small incremental change in the way we do things, but the next big leap and revolutionary changes to the way that we're doing things. And then I have the pleasure of being able to take those technologies that we've developed for our space missions and transferring them to private industry, working with those companies to actually be able to determine feasibility for commercialization of those products and help them to actually transition those products into their commercial, markets. And so strategic partnerships is a big thing that I'm responsible for as well, not just with our commercial entities and other government agencies in the United States, but I work a lot on the global stage, partnering with other countries to enable the missions of the future and doing more than just NASA missions, because we do things with medical, with medical industries and everybody else.
So I'd love to ask you this question. What do you think of since what your role, it's sort of this public-private partnership for the development of these cutting edge technologies? Like, what do you think of as sort of the government's most important role, and sort of how do you think of how to divvy that up? Like, what should the private space work on versus what should the government, provide incentives for, or what have you?
That's a really, really good question. So the way that we have been operating in the past is so many times we find that the private industry companies can't necessarily close the business case for those investments that are one and done. They really need to be able to have a profit, as we all know. And so many times for the kinds of things that we're doing, it's a first time ever doing it. And so when you're developing things for the first time and there's not the support, you don't know whether it's going to work or not. You don't know just how much of an improvement it's going to make. That is the role for the government, to be able to invest in those things, to get them to a technology readiness level where you can demonstrate the technology and capability and then transfer that over to private industry for them to take it, develop it even further, mature it to the place where they can actually infuse it into their needs and commercialize it. And so the government should not be competing on those things that private industry can actually do. We are here to kind of push the envelope to invest in those things that they don't have a business case to close to do.
And with the space industry moving so quickly, I'm interested, you're probably at the furthest frontier than anyone. And so how has that frontier moved since you've been there? When you first got there, what was mind-blowing that today's, just normal? And then where do we look to the future?
Wow. So, back in the day, so Goddard Space Flight Center we do so many different things, but communications and navigation is one of the things that we specialize in. And so back in the day, just regular communication, all of the information that's come down from the International Space Station has come through my facility at Goddard Space Flight Center. These days, back then, communication with RF frequencies and all of that was the way that you're supposed to do things. You think about cell phones and things like that, how much they've advanced in terms of communication and how much data you can pass on those small devices. These days, we just launched the laser communications relay demonstration. So you're going from, it is much, much faster communication, going from like 65, megabits per second to gigabits, 2-point-something gigabits per second. So communication has gone incredible, big leaps and incredible progression over the years since I've been in this industry. But it's happened on so many levels. So even things like the laser work that we've been able to do, having these big systems and then shrinking them down into tiny, tiny systems to go from huge platforms, billion-dollar platforms, because the spacecraft had to be so big to keep all the power on and to have all of the resources that you need on the spacecraft, to these tiny, tiny small sats that can get very, very powerful measurements and very powerful science, conduct powerful science on small, small platforms. And where we're going even from there is taking those small sats, small platforms, and doing swarms of those. So imagine doing constellations of small sats that are reconfigurable. That's what I'm working on right now, reconfigurable constellations. So you start, like, look at it for an Earth application. You start over one particular scene, let's just say, you're looking at a storm over here, you're looking at something over here. The constellation has information that can talk to each other, process the information, and especially since you are interested in autonomy, being able to autonomously take a look at the data, use AI and ML capability to do analysis and look at the algorithms so that you can process that. Have a human in the loop or not a human in the loop, but then we have another event happening over here, and then you can direct part of that constellation to move from over here to over here, or take a totally different vantage point view of another scene and communicate information back and forth, especially if you have a storm that's moving swiftly across, the nation or across the globe even. So there's so much that's changed, and I could mention like 50 million different categories, but it's just a lot that's changed. Even the landscape of the staff members, now we're in a COVID situation. So all of those people that were very, very hesitant to learn new tools and to make everything, put everything online and make it so that you can access things from everywhere, the cloud, all of that was, I'll take it or leave it, and we'll get to it when we get to it. All of that has changed. And the way that we operate at NASA is very, very different now. And so many things have changed. It's beautiful, though.
That's what we always say is crisis is a really good catalyst for innovation, because it forces you to stop and actually think, how do we do this in a better, more productive way? And if everything's going fine as it is, it's hard to break status quo.
Right. It's a bad thing that we're dealing with, but we're seeing some really good things come from it.
That silver lining that you mentioned.
Yes, exactly.
And, something you said reminded me of some of the work that we've done looking at, satellites and drones. So we've looked at how, both these two types of vehicles or machine types could be used as communication systems. And, because drones can also take images as well. I guess, have you, from our perspective, it seemed at the time like, satellites for a communications vehicle are perhaps a much more efficient instrument. I'm just curious, have you you all done any work there, or any thoughts?
Yeah, absolutely. So we're in the process of developing Earth information systems, and communication is huge when it comes to that. So taking images with drones or with any other type of satellite, we'll say, it's not the actual satellite or the imaging component that is the innovation. As we all know, that has been happening over time. Where the real innovation comes in is the algorithm work to be able to take the information from multiple systems and be able to take that to form a very, very different picture of what's happening. And so that is what we are focused on. We, of course, are developing the imaging capability and the satellite, information systems. But it is the back part, the back piece of it, where you do the analysis of that information, where the innovation really comes in, and where the benefit to all of the country and the companies that are engaged comes from. That's where the profit lies, in the behind the scenes images.
Got it. And I can imagine that the swarm technology that you talked about as well must be something that's relatively new. I guess what do you see as sort of the biggest problem that you're looking to solve, or what's the next big thing that maybe has to do with that back end operation that where do you see us in 10 years that we just can't get to today?
Okay, now keep in mind you're talking to me, and I'm focused on crazy out of the box innovation, like going to Mars and beyond kind of stuff. So when you're talking about communication and you ask me what the biggest challenge is, For me, the biggest challenges are things like, do we even use GPS in the future? Right now the GPS system has 30 satellites around the Earth, and you've got to have, 3 or 4 of them to be able to pinpoint your location. That's how your phone operates and how the GPS system actually operates. Well, we all know that we have bad players that would love to be able to take out our GPS systems, right? And so it gives people in wartime and everything else an advantage if they can actually make you blind, right? So that you can't see in the theater. And so with that being the case, how about we come up with some kind of way where we don't even need satellites to be able to navigate? How about we come up with a way to use pulsars, which are out there and they're rotating at such a regular frequency that it's like a lighthouse, light. It's like an atomic clock, actually. And so we could use those pulsars to navigate between planets. We can navigate, using totally different technology that no one can disrupt. And so those are the kind of things. I'm not thinking of the little everyday problems that we know we're going to solve. We've got to be thinking the next generation of problems that we need to address, because now is the time to start investing in those so that you'll be ready to implement them down the road.
That is incredible. Are you a sci-fi fan, or is it too close to your job to?
I am a sci-fi fan. I love all of it.
All right, we're gonna get book recommendations at the end. But then, so what is the Goddard Space Flight Center's responsibility in all of this? NASA's huge. What is this flight center working on in particular? And then I guess we can look at how that impacts the missions and how we get there.
Yeah. So when you say Goddard Space Flight, I'm going to share my screen with you for just a moment, if you don't mind. All right. So Goddard Space Flight Center, where we contribute. So there are multiple divisions within the big NASA. You have the Aeronautics Organization. It's called a directorate, the way that we have organized. Aeronautics Directorate. You have a Science Mission Directorate. You have the Exploration Systems and Space Operations Mission Directorate. And then you have a Space Technology Mission Directorate. So it's 4 different areas where we are focused on activities within the agency. The Science Mission Directorate has the focus on all of the science areas. And our center, Goddard Space Flight Center, is the largest component of the science activities for the agency. And so you will see at Goddard Space Flight Center, we are one of the very few places that get a chance to play in all 4 core science areas. So Earth science, we're studying the Earth. We're looking for ways not only to survive on this Earth, but ways to thrive and ways to really improve the quality of living right here on planet Earth. Heliophysics, studying the sun and the effects that the sun has and the interchange between the sun and Earth connection. When you think about, sending humans to the moon, for instance, when we had, the Apollo program, imagine if that program had happened, the landing on the moon, the first landing on the moon, if that had happened 1 week later, we had a big solar storm and coronal mass ejections coming out, those little spewing things that you see coming out of the sun there. If it had been 1 week later, it would have been a horrible situation because the astronauts would have died. I mean, we don't have the means just yet to protect humans while they're outside of our Earth's environment. We don't have the means to protect them from the radiation that they would have experienced from that kind of solar storm. So it's important for my center to be the one that actually monitors what is happening with the sun. And we actually give warnings to all people on the ground to be able to let them know, for all the satellites that are up there, make sure you put it in safe mode so that you're not going to be having negative effects coming from the solar storms that are happening. You probably saw the news about SpaceX and
SpaceX satellites.
Yes. And so we are working very closely with them on the investigation on the backside of that. And in looking at investments that we can make to improve the knowledge of the information that comes from the observations that we're making. So that we can give them a much more a much more accurate depiction of just how impactful those storms are. We were able to predict that that storm was happening in advance, but the implications and reasons that decisions are made to launch or not to launch during those storms is a guess about how significant or how impactful that storm is going to be once it reaches the Earth and on the way from the sun to the Earth. And so that is one of the areas that we're going to be really ramping up in coming soon. We also do quite a bit of work in planetary and lunar science. And so when you think about Mars, for instance, and Mars used to be an environment that's very much like Earth. It had oceans and water and an environment like we have. Something happened on Mars, and we need to understand what happened there so that we can know what could potentially happen here and make sure that we're protecting ourselves based upon the knowledge that we're gaining from other planets like Mars. And astrophysics, understanding about the Big Bang and dark matter and dark energy. And you probably are very familiar with the Hubble Space Telescope. That was one that was developed at my center. The next generation of the Hubble telescope is the James Webb Space Telescope, which we just successfully launched. And we were able to get it out to L2, and we've gotten everything deployed, and the mirrors are in place. So now it's a matter of fine tuning it, doing all of the configuration that we need to do, and making sure that it's focused where it needs to be focused. And in the next few months, we'll be able to see some really amazing images. We were able just this last week to get first light coming out of that. So we're very excited. It's performing just the way that we have anticipated all of these years as we were building it. And then we do support human exploration and operations through the communications and navigation activity. So I mentioned to you about communications. We are developing, a LunaNet system. So being able to have satellites and relays between the Earth and the moon so that we can actually see what's happening on the sun. We can get information to one of our relays and down to the surface of the moon. On the surface of the moon, we'll have a handheld device or a visor, a heads-up device for the astronauts to let them know of the action that's just happened, how long it'll be before it reaches them, and be able to map out how for them to get to the safest haven, underground or however we're able to protect them, so that they can make sure that they're safe with that the heliophysics or solar flare about to happen, the one that has already happened. And so then we have suborbital programs, range services. We're supporting the Northrop Grumman activities for Artemis, space communication and navigation, and then the cross-cutting technologies and capabilities across all of the science areas and suborbital platforms and ranges. And we have the only range owned by NASA out at Wallops Flight Facility. Cross-cutting technologies and capabilities is where we really focus in on those technologies that could broadly apply to multiple lines of business. And so we're looking at miniaturization, we're looking at really kind of fine-tuning, and we're looking at taking our technologies and being able to map those technologies into whole new areas to make revolutionary changes in how we do business in those new areas. And so those are our contributions there. When we talk about Goddard Space Flight Center, it is truly 6 different pieces of our center. So the first one that I am in I'm not in there right now because I'm actually working from home today, but Maryland is where we have Goddard Space Flight Center. And that is our main campus at Greenbelt, Maryland. It's got 1,270 acres of land and over 35 official buildings. That was established in 1959, believe it or not. So we are 63 years old. And then we have Wallops Flight Facility, which is located on the eastern shore of Virginia. And it's our largest in land mass at 6,188 acres of land. And that's because that is where we operate the only range that we've got. And you've got to make sure that wherever you have a range, you've got to have a big enough distance around it so that if you have a bad day, which we have had before, you're not going to hurt the families and the homes around it. You have to have a big enough clearance to make sure there are no human lives that are going to be in danger if you have a bad day.
Do you think that will, sorry to cut in, do you think that's going to change as space flight becomes more frequent, or there's always going to be this big safety net around just in case?
Yeah, you have to have the safety net. You really have to have the safety net because you're dealing with mechanical devices, and mechanical devices can be faulty. Something can go wrong, even though you've got fail-safe mechanisms in place as a backup in case it goes wrong. If it goes wrong and you have a house right there next to it and it lands on that house, the government will never live that down, and you'll be sued and everything else because you should have taken the appropriate precautions. And so we even have clear out, range in the water. So like if boats are going by, we can't even launch if there's a boat going by, just in case this thing, comes back and kills the people on the boats. And so it's very, very, very critical, no matter how many people you've got launching, to make sure you're protecting the folks on the ground as you're launching. So then also we have Goddard Institute for Space Studies, and that's what we call GISS, and that's in New York. That's a collaboration between NASA and the Columbia University. And a quick fun fact on that, the building that occupies GISS is located on the top of Tom's Diner from the show Seinfeld. I don't know if anybody watched that movie Seinfeld, but that's the same building that you saw. That's it. And then we have the IV&V facility, which is independent validation and verification, and that's the Christyl Johnson one. I don't know if any of you saw the movie Hidden Figures, but this is renamed after Christyl Johnson, who was the hidden figure mathematician in that movie. And that just has been an amazing thing for us, the movie Hidden Figure. I'm one of NASA's modern figures, so I have the pleasure of being able to go around the country for openings of that movie to talk to people in the audience before the movie started, and joining the cast and crew of the movie in several different ventures around the country. So that has been an absolute incredible thing for the future of our kids, being able to make sure that we have plenty of kids who are interested in STEM careers in the future. And that's one of my passions as well. Then also the White Sands Complex, that is located in Las Cruces, New Mexico. And while Johnson Space Flight Center really operates that, we have several complexes that are run by Goddard out there in New Mexico, and that is for the communications part of what we do. And the last piece is the Columbia Scientific Balloon Facility in Palestine, Texas, and that is where we do a lot of the balloon manufacturing activities. And then the last one that I'm going to show is just some demographics here. The center is really comprised mostly of professionals, actually of scientists and engineers, 61% of scientists and engineers. We have over 450 PhDs on the science side of the house. That does not include PhDs like me on the engineering side of the house. And so we do have about 10,000 people that are a part of Goddard Space Flight Center. And then you'll see that the technicians are about 6% and about 33% professionals and administrative. But it is a real pleasure to be there. We really promote diversity because it's so important for us to innovate there. And one of the most critical things for innovation for all of us is just making sure that you don't get to a place where you have groupthink. The place where you have everybody that looks alike, everybody that has the same life experiences, because once they get together, the solutions that they come up with are very similar in nature. We bring totally outside the box people to the table, and people who are not even involved in that particular field, and say, here's our problem. Take a look at this problem and ask me questions. And folks will say, well, why are you doing it this way? Why don't you just do this? And if you're on the outside looking in, you can easily say, gosh, it doesn't make sense that you're doing this. And then the rest of us are like, why didn't we even think of that? And it's because you're so ingrained in what's typical and what you normally do. And so we really thrive on diversity of thought. And you got to have age range diversity. You've got to have race. You've got to have sex diversity, all of that in order to get the most creative solutions to your problems.
May I ask, from a scientific engineering hiring perspective, what's the most, who are the types of people that you need the most today?
Very interesting. So that's a broad question. Can you be more specific? When you say who are the types of people, are you talking about?
I guess what fields are,
Okay.
are you aggressively this is this is sort of the team that we're always looking to add people to, or what are the most sort of in demand positions that you're looking to fill in terms of your, scientific roles?
Okay, so scientific roles is one thing, but in order to achieve those scientific goals, you need systems engineers. That is one of the most valuable commodities right now. It is so hard for us to find really good systems engineers. So when it comes to astrophysics, there are a pool of scientists out there that you can pull from, because the people in academia, really can fill some of those roles. And so we bring in heliophysicists, we bring in, planetary scientists, astrophysicists, all of it we can find. But when it comes to actually not just coming up with a concept, but going from concept to something that you can fly, that's where the problem comes in. And we really have a strong need for systems engineering skills.
I don't want to, I wish we could keep you all day to keep talking, but we're running out of some time. So on that last point, what is the current system? How do you go from idea to mission, right? Sending up a huge telescope. How do you who's asking the questions? What does that all look like?
Oh yeah. So we have similar but very different processes depending upon the class of mission. So for our small missions, there's one process. For the big missions like James Webb Space Telescope, that's a whole nother ball of wax. And so do you want me to focus on the small, or do you want me to focus on the larger?
Let's go big. Let's go big.
So the way that James Webb Space Telescope kind of came about, we have these things called decadal surveys. And so the National Academy of Science pulls together experts from across the community, from academia, from everywhere, all the different agencies and private industry experts, and they get together and they come up with a report. And that report tells you what are the most important science questions that need to be asked over the next decade. And they even go so far as to say, okay, we think that there are certain technology gaps in being able to take those kind of measurements. These are some of the technologies that you probably should focus on. And they don't get into your knickers about how to do those and even some of the details, because some of the big technologies require several small technology investments to get you there. And they don't get into all of that. But then, so once you have an idea of a measurement that needs to be made, then they do an announcement that comes out to say, these are the measurements. What are your thoughts on this? Do you have ideas? And so they solicit that from the whole community. And so from the inside, our team gets together even long before that comes out. Our scientists put together these white papers and they publish in peer-reviewed journals so that the kinds of concepts that they come up with are justified by the science community. Because if it's not something that's supported by the community, it will never be accepted. You have to be a preeminent leader in your area in order for you to be accepted in a concept like that. It's huge. And so then once we have that kind of concept together, our team gets together. First of all, it starts years before you're actually able to put in your proposal. So that proposal going in for something like this, it takes years of work before that to get ready for that. And so we start investing in technologies because they'll say, okay, Christyl, these are the kinds of things that we know we're going to need to make that measurement. We don't have that capability right now. We're going to have to go from this and shrink it down to this. And we're going to need measurements to be more accurate in order to get, more deliberate and specific results when we come back. And so we invest in those technologies. We pull our teams together. We reach out to the community and we establish our partnerships. So we've got partnerships with private industry companies. We put out an announcement and we say, okay, who can build the spacecraft? Who can build this instrument? Who can build that instrument? Who can supply the sensors? A whole bunch of different elements come together and we figure out who we can partner with in industry to be on our team. And then that team gets together and massages the concept. It goes through review processes, several review processes. And we finally get to a place where we have a package of something that we think will be really, really good. And then it goes through my internal processes for review and down select and cutting and making sure we have the right partnerships in place, reaching out to our international partners to make sure if they want to contribute something, spending their own dollars, and we partner with them to do the work. that makes it even better if we have strong partnerships around the world. So I've spent, years and years formulating those strong relationships with other countries so that we can work really closely together. And then it goes through the selection process, which is another long process on the back end.
And then it has to make it to space.
Yes.
From the outside, it's like you look at it and you're like, wow, this looks hard. And then,
It's
that's just the final, that's like the last mile relative to the whole effort that's gone into it.
Oh my goodness, yes, absolutely. It's amazing, but it's so much fun.
It sounds amazing.
Yeah.
Dr. Johnson, thank you so much for joining us today. It's incredible. You got me. I'm already excited about space, and you made me even more excited about space.
That's awesome.
So what is your favorite sci-fi? What should we all go home and read?
Well, actually, so not reading, but have you watched the latest Star Trek Discovery?
No, I haven't. I haven't seen it.
Okay.
You have to check
All right.
it out. You
All
have
right.
to check it out. Yes. And it is actually supported by my adopted mother, Nichelle Nichols, who was in Star Trek, Lieutenant Uhura from the original Star Trek. She is my adopted, not really adopted, but she adopted me as an adult in my current role. But she definitely supports this new version of Star Trek, and it has been really good. I've really enjoyed it so far.
Amazing. We'll add it to the binge
check it
list.
out.
Please do. Definitely do. It's been amazing. It's been great having this conversation with you all.
Yeah, thanks so much. We really appreciate you taking the time to chat with us. This was great.
My pleasure.
ARC believes that the information presented is accurate and was obtained from sources that ARC believes to be reliable. However, ARC does not guarantee the accuracy or completeness of any information, and such information may be subject to change without notice from ARC. Historical results are not indications of future results. Certain of the statements contained in this podcast may be statements of future expectations and other forward-looking statements that are based on ARC's current views and assumptions and involve known and unknown risks and uncertainties that could cause actual results, performance, or events to differ materially from those expressed or implied in such statements.